He's called the fixer, you know, the wolf from Pulp Fiction, which is telling you quite a bit, and he's going to be talking about application versus platform teams. Please welcome Aaron.
Thank you very much. So my name is Aaron Sempf, a bit of an introduction. I am the next-gen tech lead for AWS across Asia Pacific and Japan. Those are giving me some feedback. What does that mean? I'm focused on forward problems. So I'm looking at the problems that we're trying to solve next, not all the issues that we have now. So to that point, I need to thank the coordinators for allowing me to come and talk about anything except generative AI, because for the last 2 years, all I've been talking about is generative AI and getting tired. So today, if I can get a show of hands, who's familiar with infrastructure as code? Yeah, most people in the room, I would hope so. Who's familiar with infrastructure as logic? One, awesome. Infrastructure as logic actually comes from civil engineering. So it's a term that I borrow from civil engineering. What it means is infrastructure logic looks at civil architecture, so buildings and civil spaces, as function over form. And so it applies nicely, a bit of a duonomy between programming logic and function. So we're looking at infrastructure as logic, so function over form, as a foundation of composable architecture. Now, who has heard of the term composable architecture? Perfect. 7 people in the room. So for you, I apologize. It's going to be a recap. For everyone else, we're going to learn something. So what are we trying to solve? This is something that I've been trying to solve since before generative AI, before ChatGPT took over the world. There is let's call it a disconnect, a divide between domain teams within the platform team. There's also a divide between the applications team and the platforms team. The application team and the platform team, obviously, they're focused on function versus the implementation of said function for infrastructure. But even within our platforms team in enterprise, there's often a division between the different implementations of infrastructure, whether it be through AWS, whether it be through Azure, whether it be on premises, or whether it be third-party services. So what if there was a way to unite the domains of control within the platform and across your application teams? There is, but we'll save that for the end of the presentation. So let's take a quick look at the platform versus applications divide. So obviously applications, a show of hands, how many of you are application developers? Good half of the room. How many of you are platforms developers? A third of the room. How many of you are infrastructure engineers? Ooh, we got a few. Awesome. So there's a good mix. So hopefully this will ring true. If not, I'll be at the side of the stage. After my presentation, you can go and tell me where I went wrong. So from an application point of view, application developers are looking at function, right? We don't care about how we're implementing our function. We need authentication. We need authorization. We need to store some data. We need to process some data. So we may use some form of machine learning analysis. We may have third-party requests to, say, ServiceNow or to some other third-party provider that we use through API. Generally, those requests are made to our application team through an API. So we're utilizing REST. More often now, or more commonly now, we're utilizing GraphQL, WebSockets, other more bidirectional ways of communicating between our platform and our applications. But the platform are the ones who are generally writing the business logic to fulfill the requests for our authentication, for our data store. And then within our platforms team, there is some form of configuration for the implementation of our infrastructure. In this case, let's say our enterprise is using Azure Active Directory, and so we want to authenticate on Azure Active Directory, but we've got a whole lot of our data in AWS, so we're using relational data services on AWS. There's a problem here when we get into different domains. So now we're looking at authentication, we're looking at RDS, we're looking at ML. We are looking at the different areas where we're implementing our infrastructure. So we've got Azure for our Active Directory, we've got AWS for our RDS, we've got ServiceNow for servicing tasks, or it could be any other third-party provider for Atlassian, for Jira, or whatever we're doing in terms of sending data to coordinate something and bring it back. This generally creates multiple responsibilities within the platform team. Obviously, there's a divide between our application team and platform team already. We're looking at functional versus implementation. We're also, within our application team, looking at media. We're looking at desktop. We're looking at mobile. We're looking at web. So there is a difference between the development of the application, how we're developing it, but we're still looking at functional. This divide of responsibilities within the platform team often creates the antithesis of DevOps. We're starting to break people into silos. We're breaking people down between you're the Azure team, you're the AWS team, you're the ServiceNow team. We're starting to break people into their domains to facilitate the logic for the requests that are coming through from our applications and facilitate the implementation of the architecture. So, in the past, we've tried to solve this problem with team architecture and different application architectures. Big question mark here on, is the problem solved? You may not have seen my talk at reInvent last year on reinventing the backend for front-end pattern. Backend for front-end pattern did go a long way to helping teams connect horizontally in terms of now the same team may be facilitating the desktop front-end application along with the API for the desktop backend, and the backend is being built specifically for the application, not specifically for the implementation of the infrastructure. However, there's still a divide within the platform team around backend, so developing the business logic and then connecting to the implementation of the services. But then the platform team also became much more about governance and understanding our security and AppSec and approvals and going through architectural review, and became a very cumbersome process to go from application through to infrastructure that we want to use through all of these layers of platform. So while the architecture helped the applications unify, it didn't really help the platform team unify. It still created that division between all of the domains. So let's take a jump quickly, because I've crammed an hour talk into 45 minutes, so I'll try and go through as quickly as we can. Let's take a look at the history of infrastructure as code to understand where we're going. So in the very beginning, I can see some grey beards out there, so you're probably around the same age as me. You remember when we actually had to physically stand up a server. We would physically move a server into our data room, which wasn't in some big data warehouse. It was on premises, generally within the IT and ops team, in the back, with some air conditioning. This was our traditional practice of provisioning new services. We would first have to manually install the server, and then we had our runbooks and playbooks on what do we need to install, what is the patching we need to do, what is the platform we're building, so what is the supporting OS, what is the supporting applications and services and the like. This was a very manual process, obviously. So from here, often when we were standing up something new, as we advance, we have our playbook from the last time we did it, and we'd find, oh, something's changed. We no longer have the same setup. We no longer have the same requirements. We need to implement something new. And more often than not, it was go and ask Bob. He knows, because he was the last one to do it. And he didn't go and update the playbook or the runbook or the documentation that we had. So ask Bob and just hope that he hasn't left the company or that he's not on leave. So we went a step further. We got Bob to start writing scripts. Now we have our bash scripts, allowing us to run scripts of code to go and do the installations we need, to go and configure the things that we needed. But the problem with scripts is they only were designed for very simple installation. They're not designed for complex infrastructure environments. They're only designed to patch, install, and do simple things. Yes, you can do a fair amount of logic within your bash, but it's not designed for complex infrastructure. So then we invented declarative. This is where most enterprises stopped. The use of Terraform, the use of CloudFormation, if you're on Azure, then the use of ARM, to document your infrastructure as a declarative list of infrastructure that I require from my application, and I can deploy it through an infrastructure engine. So in this case, CloudFormation template runs through CloudFormation, deploys into AWS. Perfect. I've now got automation of my infrastructure, but there was still a problem. The problem was The declarative infrastructure as code was written in a declarative way. So we have YAML or JSON, and we have thousands of pages for a large enterprise or tens of pages for a small startup of YAML that nobody can read. Who here loves reading YAML, yeah? Perfect. 2 infrastructure engineers love reading YAML because nobody else wants to read it, so it makes them valid. I call these guys YAML engineers, right? Or JSON engineers, because everything they need to do is declared in a document, in a text document, but they are so smart because they remember every single configuration, every single variation, every single integration that they need to remember to write a YAML document. This is where we got into generators. So GoFormation, Troposphere, these are the engines that allowed us to start generating our declarative templates by having our libraries of all of these components, all of these configurations, to be able to generate the templates that we needed to go and do our deployment. But coming from a distributed systems engineer perspective, I'll always lean towards writing code. And this is where we've moved into abstractions. AWS CDK, Pulumi. Who's familiar with Winglang? One. Our YAML engineer is familiar with Winglang. Make a choice. These languages are the imperative languages that allow us to use our programming language to make our infrastructure declarative. So we can still declare our infrastructure. It goes through a generator, so it transpiles from code into template and allows us to deploy. So this is where we're at now in terms of abstractions. We're getting there into generative AI, and this is the next level, but this is not a Gen AI talk, so I'll leave that for another session. However, as I said before, declarative is generally where most enterprises stopped. So what is infrastructure as code? Or more importantly, why is infrastructure as code? The whole purpose of infrastructure as code is to automate. The whole every historical change in the way that we've implemented our architecture is making it easier, is not just to deploy, but making sure that we iterate on the best practice. When we learn something about securing something and hardening something, we don't want to have to redo that every time. We create a script for it, or we create a template for it, or we write code to secure it, so when we deploy, it's the same. We reduce the configuration errors. When we have declarative all the way up to imperative, or the code that we're writing in CDK, we write one library. We write one set of code, we compile it down, or we wrap it into a library object, and we reuse it. And to the point, reusability creates duplicity. We can now duplicate our environments across applications, across whatever it is that we're trying to deploy. So, why did enterprise get stuck at declarative? What is the difference here? Declarative versus imperative. Hands up, anyone not familiar with what imperative means? Perfect, thank you. You're all software engineers, except for those 2 YAML engineers. The difference here is when we go declarative, as I said before, our YAML engineers have to remember everything. It's a declaration of, or the description of, the resources that we want to deploy and their configuration and any points of integration and any additional information that is required. For imperative, we're describing the steps of the solution that we want to develop. So it's the steps of the system as opposed to the declaration of the individual resources. Generally, the difference between the two is it's simple. Writing YAML or writing JSON or writing a template is I can see simply what I'm deploying, but simple from the complexity of the system that we're developing point of view. Not simple as in it's easy to remember. I'm not sure if you can see that on the screen, but as long as you know all the components and settings, right? There is a wealth of information that you need to remember, and that's not simple. But when we get into complex situations, especially where we have a SaaS application that needs time-sensitive resources. We may have an object database that we need for doing some processing of information that we want to store there temporarily, but as soon as that data has been processed, we want to blow that away because it's of the sensitive nature of the data, Or it could be that we have a tenant-based system where we want to stand up different resources for a tenant, which is not going to be there at the beginning of our infrastructure deployment. So when we get into complex situations like this, we generally need to lean towards imperative, because as platforms engineers, if we're not doing it within our infrastructure, we're writing it within our business logic. And finally, the declarative is an end state instruction. So this is what I want you to deploy, go and do it. For imperative, order of events is critical. I'm not saying that declarative can't have an order of events, because yes, we will have dependencies between infrastructure. But within our infrastructure template, we may have some very simple this first, then this, then this. It's still simple. It's still the end state instruction. For our order of events, this is where I'm talking about the critical nature of timed resources, or when we have a tenant that needs something extra based on a condition. Now we're getting into complex systems, and the order of events is critical in so much as we may need to stand up a Active Directory before we can, a subtree before we can go and deploy other resources. So let's take a very quick look at declarative. Can the YAML engineers tell me what we're deploying here? I'm not going to ask you to call it out, it's fine. This is what we're looking at in terms of YAML, right? So the difference here when we get from declarative is that we have a stack. Generally we call a template a stack. These are the resources I'm going to deploy. When we get into complex enterprise systems using declarative, we have many stacks, and those stacks have a one-to-one representation of the group of resources that they're deploying. So now, going back to our platforms, the breakdown in domains, now we have one domain with one set of templates that is deploying into Azure, another domain which is another set of templates which is deploying into AWS, another domain with another set of templates that is deploying to name other third-party API, yeah? But it's a stack to resource relationship. When we get into imperative, we now move the one-to-one relationship from the stack up to an app, and say this one application can now contain multiple stacks which will have multiple resources. So the stacks remain the same, they still are the declaration of resources, but within an app we can now apply imperative logic that says for this region deploy this, for this region deploy this. So we can have a one app, multiple stack, but we may not have to write each stack. We can then start to use logic. Infrastructure as logic, to then say for every region that I have this global table, go and deploy these resources, and it will cycle through and use our logic to go and deploy our resources into the regions that we want. But looking at this code here, it doesn't look very imperative, does it? It's still very declarative. We still have we're declaring our app, we're declaring, what are we declaring here? A stack, we're declaring a Lambda function, and we're declaring an API. So this is going to deploy an API backed by a Lambda function. That was the first diagram that I showed you of the platform, right? Application to logic. But for those of you who aren't familiar with CDK, what we're missing here is the logic is in the constructs themselves, right? So we have underlying logic that says, when I say handler is the name of my function and I drop handler on my REST API, there's a lot of logic under the hood that's saying, right, for this Lambda, you need to set up a security policy to allow the API to execute the Lambda, and whatever else is required to make this all work, go and do it. So there is logic there, but there's an extension of logic that we can use. So hands up for those of you who are familiar with CDK or use CDK quite often. Cool, third of the room. Now hands up those of you who aren't using the standard scaffold and writing your own constructs, writing your own libraries. One person, two people, awesome. You guys can leave, the rest of you know the rest of what I'm gonna say. Here, now we're getting to imperative. You do not have to use the standard construct or the standard scaffold, which is the app, stack. You can do, who's familiar with infrastructure from code? Yeah, infrastructure from code, one person, perfect, is runtime infrastructure. So we have applications running now, and as we need infrastructure based on runtime conditions, we can go and deploy infrastructure. That's a whole other talk. There's an hour's worth of stuff to discuss there, but it's using the same framework. It's using the same code, CDK or Winglang or Pulumi. We can now start to add our logic into our stack to say, based on a query, I'm going to go and query how many tenants that I have, and I'm going to deploy some new infrastructure, and based on those tenants, I'm going to go and deploy it into each of their accounts. Or it could be a shared account. I'm going to deploy this across each region. For every region, I have tenants. We can now start to write logic that says, based on conditions outside of what I'm deploying, conditions outside of my application, I can now start to implement not just infrastructure, but solutions, workflows, whatever you want to call it, that bring together multiple components within AWS. All right, third time, last time I jump. A few of you put your hand up on they know what composable architecture is. You want to stand up and explain? No, I'm kidding. For those of you who don't know what composable architecture is, Andy Jassy, founder of AWS, under Jeff Bezos, now CEO of Amazon, has famously always said that AWS is a company of building blocks. That's essentially what composable architecture is. It's building blocks. But I want to take a concept that maybe some of you are familiar with called atomic design. What is atomic design? So at the very bottom level, we have atoms. Atoms together make up molecules. Molecules together make up organisms. You see where I'm going here? So we're looking at something that it's its very bottom unit of compute, or very smallest unit, which makes up the next level, which makes up the next level. Where I stole this from is Brad Frost. And everyone familiar with Atomic Design by Brad Frost? The way it's explained, there's also levels beyond organisms, but these are the ones I want to focus on for now. If you look at the components of the front-end application, we have an icon, we have a text box, we have a button. These are atoms. Together, when we put them together as a search input, now they're a molecule because they form a function. Remember, infrastructure is logic, is function over form. As an organism, it's multiple functional components together, forming a navigation bar in this case. Let's consider this from a code point of view. What are the atoms of code? Atoms of code are generally our single lines of logic. So it could be something as simple as a calculation, or it could be calling a helper library, like a string manipulation or a math function or something. Molecules then become configurations of atoms of multiple lines of code that form some greater logic. So that's our functions and methods. It could be forming some base level state. Now we have memory between our lines of code based on variables or functions that we're setting within a class. But that brings us to organisms. So our organisms are now made up of functions or methods within our classes. Or it could be groups of classes together forming a module. Keep that in mind, because now I'm going to jump to component-driven development. It's the same, but it's different, right? So for those of you familiar, I've still got 10 minutes, so I'm going to run through this as quick as I can. For those of you familiar with CloudFormation templates, that's where CDK comes in. We have a one-to-one relationship with an L1 construct. So an L1 construct is essentially a CloudFormation template that has been imported into the code language of your choice at a one-to-one level. So it's pure declarative. It doesn't have any logic. It's not imperative. It's just the object-oriented equivalent of a CloudFormation template. These are automatically generated. So when we release new services, we automatically generate the one-to-one relationship for CDK, for those of you using CDK, and release them as an L1 construct. But generally, the CDK team will then try and create what we call L2 constructs. So these are high-level service constructs. So if we had CFN S3 as a bucket, or dot bucket, that's your CloudFormation template. But we want to get rid of the need to declare everything, so these level 2 constructs are all the helper logic. All the logic included into the construct to give you the security you need, to give you the helper functions for allowing a Lambda to read from the bucket. All of the things that you need to make it more functional and less form. And then finally at the top layer is purpose-built constructs, and that's where these few people in the room using CDK, this is where they exist. They're building not just constructs of L2 components together, they're building their opinionated abstracts. So these are their solutions, these are their function over form. Now bringing it back to molecules and atoms, the services we could consider atoms. So yes, there's a bit of a difference between where we're looking at it in code, but when we think about declarative versus imperative, now the single lines of code, atoms, are the same as our declarative It's essentially a variable holding a whole lot of information about a resource that we want to deploy. It merges into L2 constructs because some are complex, some are very not. And then molecules, I haven't gone as far as to say that L3 constructs are organisms because that's the applications that we're building. The applications are the organisms. So let's quickly run through this to get to the important bit. As I said, one-to-one level L1 construct. This is what an L1 construct looks like. S3.cfn bucket. So anything with CFN is a CloudFormation template import. That synthesizes into a CloudFormation. So you can see as the CloudFormation for the YAML engineers down the bottom here, that's a resource with a bucket name of my bucket. That one line of code will compile down or transpile down into, correct term, synthesize into the CloudFormation template, which would deploy a bucket. However, is the bucket open to the public? Is it secured? There's all these other things that we need to know, so we create our L2 constructs. L2 constructs now have the level of configuration which we call sane defaults. So you can go and deploy something as a sane default without adding any configuration that'll say, all right, it's a closed bucket. We don't want to open it to the world because then you'll have people reading your personal bucket business. As an example, when you do a VPC is actually a combination of other smaller modules that make up your VPC, your virtual private cloud, which is an API, sorry, not an API gateway, an internet gateway, subnets, all of your CIDR ranges, all of that's configured into one line of code for VPC. That's an example of an L2 construct, adding the additional logic, adding all of the same defaults. A stack is, I mentioned it before, a configuration of individual L2 components. So for those of you who are using the scaffold, you're generally creating stacks. Here's an L2 construct. I want it to talk to this L2 construct. I want it to talk to this L2 construct, and I'm going to deploy it. So we've got a bucket which is talking to, or a Lambda which is reading from a bucket and writing to a DynamoDB database. That's a construct. That's not an L3 construct. That's a stack construct. When we get into L3, we're now talking about these opinionated solutions, right? So I don't have to write all of those components, which is my VPC plus my Elastic Load Balancer plus my Fargate service to manage my EC2 instances plus my ECS task and deploying the ECS task just to run containers in ECS. I don't have to build that as a stack and then have to rebuild that every time we want to do some containerization. I can go and build my ECS pattern library and create an application load balancer Fargate service. And every time I want to deploy from the platform point of view a new container into a microservice environment, I just use that one construct and say, here's my image, go and deploy. I don't need to rewrite the stack every time. That's the important part. When we get into our, I'm going to go through this very quickly because I think you all get the point of 1, 2, and 3, and stacks versus constructs, right? So multiple constructs at the L2 can make up a construct, an opinionated construct, or they could be deployed as a stack as themselves. Stacks come under apps, so we have multiple stacks under an app, and then an app is synthesized down to deploy into CloudFormation, which deploys out. Now, the important part that I'm running out of time to tell you. Oop. So we did go through services, are your atoms, just drumming this one in so you remember it. Molecules are your constructs. So what is a construct? We're talking about functional components, not end-to-end solutions, just functional components. Give me some authentication. Give me some data store. Give me some ML with an output of this, some analysis. If I give you this input, give me that output. That's all I care about. Your organisms are your end-to-end solutions. These are the patterns. So now we're talking about, what have we got here? View, image, and text. So now we're talking about multiple functional components built together to provide some kind of business value. But bringing it back to the very beginning, how do we solve for multi-domain control, right? So what if there was a way to unify doing all these templates in Azure, doing all these templates in AWS, working with ServiceNow and their APIs? A little known secret that's been around for many, many years that we have traditionally not talked about because we don't want you to go and use the blue one or the red one, we just want you to stay on orange, is CloudFormation Registry. We ourselves use CloudFormation Registry to provision external integrations. So if anyone familiar with Amazon Location Service, there's data providers under the hood for Amazon Location Service. You might be using Esri. If you're familiar with Esri, they have their own Esri ArcGIS cloud. We're not hosting all of this on AWS, but when you select Esri as your provider, we're setting up an account in their SaaS environment through the AWS console. How we do that is through CloudFormation Registry. So we can create extensions of custom logic, so that's the build, rollback, destroy, all of the deployment mechanisms for external integration through the CloudFormation Registry. And we can call any external API. It provides, well, they say it provides a better developer experience, but this is the developer experience, right? So we're going back to our YAML, we're going back to our declarative infrastructure as code, because everything here needs to be declared, but here we also mix in logic by having our deploy lambda. So it may call some level of API outside and provision the Azure client ID, the tenant ID, the client services, and everything it needs to integrate with the ARM APIs managed through CloudFormation Registry extensions. This is the UI or the console look at it. So you can see here I've got a proof of concept Azure blob storage. So I'm provisioning a blob storage in this example through CloudFormation extension. So let's get a little bit into that. As an L1 construct, so now we're going from creating an Azure blob storage container CloudFormation extension instruction. Remember I said every CloudFormation template has a one-to-one relationship with CDK. Now these aren't automatically generated, but when you go and create your extension, you can import it into CDK. You now have a level 1 construct for something outside of AWS on Azure in your third-party API that you can then configure in code to work with your existing code base. That's your atom. We can move up the stack again. We can wrap that in helper logic. We can now provide the security and state information that we need, the integration information that we need, any little helper logic that we may need inside that L2 construct so that we make it easy for our application developers to consume and say, I need to drop something in Azure Blob Storage. I have a file upload, hit upload, it's now in Azure Blob Storage. They don't care about the implementation. They only care about the function. The way we do that is through providing them the logic. So multiple L1s, or multiple L2s, sorry, make up a stack. And in this case, multiple L2s can make up our L3, our molecule. So if we look at having an Amazon S3 bucket with a Lambda to read from that, and anything I drop in that bucket, I'm going to drop in blob storage. So instead of creating a stack for that, I wrap that as a construct. So it's now just a class that I can reuse. And the important part here is, this is now where the platform teams are starting to hand over functional control to the application teams. The platform teams are now able to provide the functional output that the application teams need instead of provisioning an API and saying, here you go, make a request to this API and we'll go and provision you some infrastructure. You say, here's a library that you can consume in your SDK that will give you the infrastructure that you need, but all you care about is the function. So I can now start to use those classes, use those libraries for the function that I need as an application developer, and then the platform team, through deployment, will deploy the infrastructure. We'll get to that in a sec. I wanted to show off, it's going to be on a different screen. Tried this earlier, and for some reason I can't extend desktops, so let's look at it here. This is the implementation of that S3 bucket, Lambda reading from an S3 bucket to Azure Blob Storage, all deployed through an individual class in a CDK application deployed through my CDK pipeline. You can see I'm uploading 3 files, and the reason I recorded this is because obviously I'm not going to do a live presentation because the demo gods don't like me when we do it live. We're going to drop those 3 files into an S3 bucket. That's going to trigger the Lambda. Has it uploaded? Yep, it's going to trigger the Lambda. Once it's in the S3 bucket, uploading. Perfect, there, we can see it's there. All we need to do now is go onto the Azure Blob Storage side and refresh. Come on, refresh. And there we go. We now have 3 files in Azure Blob Storage. We never once went into Azure, we never once touched our Azure environment APIs. All we did was developed a very simple construct that allowed the application developers, in this case, to deploy the components that they needed and upload a file into the S3 bucket. Let's try to play again. No, next. All right. So as I was saying before, instead of through API, so you remember back to the first slide where we had the API to logic, logic to infrastructure, whether it's configuration, whether you're using CDK to deploy, whether you're using declarative templates to deploy. Now we can provide libraries to the application developers who only care about the function, which are molecules, so they can say, I want authentication library. I don't care how it's implemented. The platform team definitely does. So the platform teams are the ones who are developing these constructs to then be deployed through the platforms team. So now we are turning the platform team into the compliance. So we're looking at the AppSec approval, the compliance approval, the security approval, all of that controlled through libraries that our application developers can consume in SDKs instead of API integration. Now that being said, they still have APIs between the application itself or the device that it's running on and the actual platform, but those APIs are the backend for frontend. So it's a specifically designed backend for the application we're developing. So it's not breaking away from the backend for frontend pattern. It's allowing the platform teams to manage the backend for frontend pattern more succinctly or with better engagement across the application team. Because now they are provisioning the logic and making the authentication talk to the data store within the application. And at the back end, all of the platform team care about is our implementation. And now they're also our DevOps team, or our CI/CD team. So the platform team now manage the deployment of the applications. The applications teams at the very beginning may just make a request for a Git repository, and then the rest of the platform team set up all of the deployment pipelines based on their practice, their process, their security, and then it allows you to deploy using constructs into any different environment. Where does this lead? So obviously, better ownership and engagement across the organization. So now application teams aren't fed up with the platform team going, why is it taking you 3 weeks to deploy a simple database? I need it now. Before I can even start writing my scripts to talk to it. Well, now the platform team can say, you know what, you just tell us the structure of the data you need, you provide it through this construct, and we'll deploy it when you're ready to deploy into your test environment. This, when we can get faster to market through our platform team and our application team, when they're happy, means we get a better customer experience. Not just the end customer, so those who are consuming the application, but customer experience. Your applications teams are the customer of your platform team. Where this also leads, and I said I'll only mention GenAI once, right after this one, is I'm sure all of you are familiar with low-code and no-code solutions and how bad they've been. Nobody uses low-code, no-code solutions except for lower-end integration where there's a lot of adapters, and there's a whole talk on this that we could do on the side. This allows us to now be more, what do you call it, more, I forgot the word that was in my head before, allows us to dictate, is not the word I wanted to use, how our infrastructure is going to deploy, and we can now wrap drag and drop over the top. So we can say, here's a construct that we're going to deploy based on drag and drop. This one's going to integrate with this. So now we're writing the drag and drop no code over the top of our underlying code infrastructure, because it's now becoming infrastructure from code and not infrastructure as code. And finally, generative AI. Yes, I have to talk about it. Deterministic control of AI-assisted code generation. If we're training our AI assistants on the lower level code and then we ask it to do something, obviously it's going to give us the lower level code. But if we're training our AI assistants on the constructs and the libraries as an enterprise that we're using, now it's value-based generation. I want something to do this functionally. It's going to give you the libraries and the integration of those libraries for infrastructure from code. So now it's going to generate the logic that I need, so the form over function, but we can determine what the infrastructure at the end will be. So deterministic versus non-deterministic. Generative AI is very non-deterministic. It will change as the models evolve, but if we're teaching it on a deterministic framework, then while it gives us the value, at the end of the day, our platform teams are happy because whatever the generative AI generates is going to be the infrastructure that they've approved. And if you want to get started using any AWS generative AI services like QDeveloper or CDK or anything that I've talked about today, please look at the QR code and sign up for a free skill builder, sorry, not skill builder, free builder ID to get started. This will help you, if you don't have an AWS account, you get a free account for 12 months and you can play around and play with some of the things I've talked about. Thank you very much.